All right, so ready to dive into something pretty elegant today.
Always up for an elegant solution. What are we tackling?
Red-black trees. They're kind of a fascinating way to keep things organized, especially when we're talking about data structures that are constantly changing.
Ah, yeah. I see where you're going with this. Keeping those binary search trees nice and balanced.
Right, because as you know, with a regular binary search tree, you can search through it super fast. But the problem is if you start adding or deleting stuff, it can get, like, lopsided.
Yeah, it can basically devolve into just a really long list.
Yeah,
Not very tree-like.
exactly. Not efficient at all. So red-black trees are here to save the day. They have these built-in rules that make sure the tree stays balanced. So no matter how much you mess with it, adding stuff, taking stuff away, you can always find what you're looking for quickly.
And that's really the key, right? It's all about making sure those fundamental operations like searching and inserting and deleting all stay fast, even as the data set grows.
Absolutely. So today we're going to break down exactly how these red-black trees work. We're going to go deep into the rules that govern them, why they work so well and why they're so important.
Great. Should we start by maybe clarifying what a red-black tree actually is?
Yeah, good point. I mean, the name itself is kind of quirky, right? A tree with colors. So lay it on us. What's the basic definition?
Okay, so at its core, a red-black tree is still a binary search tree, which means for any given node, everything to the left is smaller and everything to the right is bigger. That part's familiar.
Right, the classic binary search tree setup. Got it.
But what makes it a red-black tree is that we add this extra bit of information to each node, which is its color. And the color can be either red or black.
Okay, simple enough. So we've got this binary search tree, but now each node's got a little color tag on it. But I'm guessing the color isn't just for decoration, right?
Not at all. The colors are how we enforce these specific rules that keep the tree balanced.
Aha, the color-coded balance enforcers. So tell me, what are these critical properties, these rules that every red-black tree has to follow?
Right, so there are 5 main properties. And they might seem pretty straightforward at first, but the way they work together is really clever. So property number 1, like we already said, every single node in the tree has to be either red or black.
Okay, that one's easy enough. Every node's got its color badge.
Exactly. Property number 2, the root of the entire tree, the very top node, always has to be black.
So the head honcho node is always in black. Got it. What's next?
Property number 3 has to do with the leaves of the tree. Now, in a red-black tree, we actually use a special sentinel node to represent all the leaves. And this sentinel, we often call it T-nil.
T-nil.
Yeah, it's basically a placeholder that sits at the bottom of all the branches, even where you normally just have an empty space or a null pointer. And the important thing is this sentinel node is also considered black.
Ah, so even the empty spots are accounted for. They're part of the color scheme. That's a neat trick.
It really simplifies things. And this brings us to property number 4, which is super important for maintaining that balance we keep talking about. If a node is red, both of its children have to be black. No 2 reds in a row.
Okay, that's a really interesting rule. So a red node can't have red children. It always has to have black children.
Exactly. And this is crucial because it prevents long chains of red nodes.
Hmm.
You can picture it, right? If we had a bunch of red nodes in a row, that part of the tree would get really long and spindly, and that's exactly what we're trying to avoid.
Yeah, that makes sense. It's like the color rule is forcing the tree to spread out more evenly, but we still have one more property, right?
Right, the 5th and final property is all about the concept of black height. It states that for any given node in the tree, if you follow any simple path from that node down to any of its descendant leaves, which are represented by those sentinel nodes we talked about, all those paths have to contain the same number of black nodes.
Okay, black height. That sounds pretty fundamental to how these trees stay balanced. Break that down for me a little more. What does it mean, and why is it so important?
Imagine you start at some node in the tree. Now, there could be multiple paths you could take to get down to a leaf, right? What this property is saying is that if you count the number of black nodes along each of those paths, that count has to be the same for all of them. And that count is what we call the black height of that starting node. And the black height of the entire tree is just the black height of the root node, the very top one.
All right, so it's like every path from a node has to have an equal blackness to it. But how does that actually help keep the tree from getting all out of whack?
Well, remember that 4th property, the one about red nodes always having black children. That plays a key role here. Think about it. If we have 2 paths starting from the same node, and they both have to have the same number of black nodes, the only way one path could be significantly longer than the other is if it had more red nodes. But that 4th property Prevents us from having too many red nodes in a row.
Ah, I see. It's like a double whammy. The black height rule makes sure the black nodes are evenly distributed, and then the red node rule prevents the red nodes from messing that up.
Exactly. And it's this interplay between those two properties that really guarantees that no path in the tree can be excessively longer than any other path. The tree can't get too deep or too skewed to one side.
Okay, so these color rules, they're pretty clever, but what's the payoff for all this careful color coordination? Like, why is this balanced structure so important in the big picture?
The big payoff is efficiency. And by that, I mean the speed of all those operations we keep talking about. Because of these 5 properties, a red-black tree is guaranteed to have a maximum height that's proportional to the logarithm of the number of nodes in the tree.
Logarithm. Now you're getting all mathy on me.
It's not as scary as it sounds, I promise. The important thing is that because the height of the tree is kept under control, it means that all those key operations, like searching for a particular element, finding the smallest or largest element, adding new nodes, removing nodes, they all run in what we call logarithmic time. And that's super fast, especially when you have a ton of data.
All right, logarithmic time, good for speed. So essentially, these red-black rules are like a recipe for a super efficient data structure, one that can handle a ton of data and constant changes without slowing down.
Precisely. It's all about maintaining that balance to keep things running smoothly.
Now, what happens when we actually start adding or removing stuff from the tree? I mean, that's when things could potentially get messed up, right? Like, how do we make sure that after we insert a new node or delete an existing one, the tree still follows all those red-black rules?
You're hitting on the key challenge with red-black trees.
Yeah.
So when we insert or delete a node, we might end up violating one or more of those red-black properties. And that's where rotations come in.
Rotations, like we're spinning the tree around?
Sort of. Rotations are like these special moves we can make. They're basically local restructuring operations that allow us to change the links between nodes in a very specific way.
Okay, I'm intrigued. What kind of restructuring are we talking about?
There are 2 main types of rotations, a left rotation and a right rotation.
Sounds kind of like a dance move.
It is a bit like that. So imagine we have a node, let's call it X, and it has a right child, we'll call it Y. A left rotation on X would basically pivot the structure around that link connecting X and Y. So after the rotation, Y becomes the new parent of X, and if you had a left child of its own, that child would now become the right child of X.
Wait, so we're basically swapping the parent and child and shifting things around a bit.
Exactly. And the key is this reshuffling. It's done in a very specific way that preserves the fundamental property of the binary search tree, that whole smaller on the left, bigger on the right thing. The order of the elements remains correct.
Okay, I'm starting to see how this rotation thing could work. So if a left rotation shifts things, well, leftward, I'm guessing a right rotation does the opposite.
You got it. A right rotation is just the mirror image, the symmetrical counterpart of a left rotation. It would be performed on a node, say Y, that has a left child, say X. And after the rotation, X would be the new parent, Y will be its right child, and any right child of X would now be the left child of Y.
So basically, we can use these rotations to kind of nudge things around in the tree, swap parent-child relationships, all without messing up the overall order of the elements. Pretty neat. And these rotations, they're not too computationally expensive, are they?
Not at all. They're actually very efficient operations. Each rotation only involves changing a few pointers, so they take a constant amount of time, no matter how big the tree is.
Good to know. So we've got the rules that define a red-black tree, and we've got these rotations that let us tweak its structure locally. Now let's talk about the dynamic part. Adding new nodes. How do we handle that while still sticking to all those red-black rules?
Okay, so when we want to insert a new node into a red-black tree, the first step is actually pretty familiar. We use the standard binary search tree insertion procedure.
So we just find the right spot for the new node, just like in a regular binary search tree.
Exactly. We traverse down the tree, comparing the value of the new node to the existing nodes, and we keep going until we reach an empty spot, which is represented by one of those T-nil sentinel nodes.
Right, those black placeholder nodes at the bottom of the tree.
Exactly. And that's where we insert the new node. But here's the key part. When we initially insert the new node, we always color it red.
Always red. Why red and not black?
That's a good question. It has to do with minimizing the potential disruption to the black height property. Remember, the black height has to be consistent along all paths.
Yeah, that's one of the key rules.
So if we were to insert the new node as black right away, we might end up increasing the black height on some paths, but not others, and that would violate the property. By starting with red, we're basically saying, hey, this new node isn't affecting the black height just yet.
Okay, that's clever. So starting with red minimizes the initial disruption to the black height. But I'm guessing there's a catch. It can't be that simple, can it?
You're right, there's a potential problem. By inserting a red node, we might create a situation where we have two red nodes in a row, which violates that fourth property, like if the parent of the new node was already red.
Ah, a red-red conflict. So what do we do about that?
That's where a special procedure called RB insert fix UP comes in. Think of it as the cleanup crew. Its job is to restore the red-black properties after we've inserted the new node.
Okay, the red node fixer-upper. I like it. How does it work?
So RB insert fix UP basically goes through a loop, and in each iteration of the loop, it examines the situation around the newly inserted node and figures out what needs to be done.
What kind of situations are we talking about?
There are three main cases it considers, and each case has to do with the color of the inserted node's uncle.
Uncle. Hold on. Family relations in a tree.
Yeah, it's just a way of referring to nodes. So the uncle of a node is basically the sibling of its parent.
Got it. So we've got our new red node. It might be causing a red-red conflict, and we're looking at its uncle. What are those three cases?
Right, so case one is when the uncle of the inserted node is also red. In this case, we can actually fix the problem pretty easily just by recoloring. We change the parent of the inserted node to black, we change the uncle to black, and we change the grandparent, that's the parent of the parent, to red.
So we're basically shifting the redness upward.
Exactly. And by doing that, we might have moved the conflict up to the grandparent, so we continue the loop and check the situation around the grandparent now. Now, case two happens when the uncle is black and the inserted node is a right child.
Okay, so a black uncle and the new node is on the right. What then?
In this case, we do a left rotation on the parent of the inserted node.
A left rotation, one of those restructuring moves we talked about.
Exactly. And this rotation sets things up nicely for case three. So case three is when the uncle is black and the inserted node is a left child. And this is often where we can actually resolve the conflict entirely.
Okay, so black uncle, new node on the left, the grand finale.
Pretty much. In this case, we change the parent's color to black, we change the grandparent's color to red, and then we do a right rotation on the grandparent. And typically after this, everything's back in order, the red-black properties are restored, and the loop ends.
So we've got recoloring, we've got rotations, all working together to keep things balanced, and all of this is happening super fast, right?
That's right. Each iteration of that RB insert fix you loop only takes a constant amount of time, and the number of iterations is limited by the height of the tree, which we know is logarithmic because of those red-black properties.
Okay, so insertion checked. But now let's talk about the elephant in the room, deletion. I hear that's where things get really tricky.
You're not wrong. RB delete, the procedure for deleting a node, it's definitely more complicated than insertion, but the good news is it still manages to maintain that logarithmic time complexity.
That's good to hear. But what makes it so complex?
Well, it builds upon the standard procedure for deleting a node from a regular binary search tree. But it has to be a lot more careful because of all those red-black rules we have to maintain.
So walk me through it. What are the key steps?
Okay, so first, RB delete identifies the node that needs to be removed. Let's call that node Y. Now, if Y has two children, we actually find its successor, the node that comes right after it in sorted order, and we use that node to replace Y. Then, we remove the successor from its original position.
So it's like we're swapping the node to be deleted with its successor and then deleting the successor instead.
Exactly. And the reason we do that is because it simplifies things. The successor is guaranteed to have at most one child, which makes the actual deletion process easier.
Okay, that makes sense. So we've identified the node to be removed, or its successor, and now it's time to actually delete it. But where does the whole red-black business come in?
The crucial thing here is the color of the node that we remove. If it was red, we're actually in good shape. We haven't messed up the black height property because red nodes don't contribute to the black height count.
Ah, so deleting a red node is a piece of cake.
Pretty much. But if the node we remove was black, that's where things get tricky. Because now all the paths that used to go through that black node, their black height has decreased by 1.
And that violates one of the core red-black properties,
Yes,
right?
exactly. So we have to somehow compensate for that missing black node.
How do we do that? Do we just, like, recolor a bunch of nodes?
It's a bit more involved than that. What we do is we conceptually associate what we call an extra black with the node that replaces the deleted node. Let's call that replacement node X.
An extra black. It sounds like we're playing some kind of color coding game here.
It's more like we're keeping track of a deficit. This extra black is a marker a reminder that we're missing a black node along certain paths, and we need to fix that.
Okay, I'm following so far. We've deleted a black node. We've potentially messed up the black height. And now we've got this extra black tag on the replacement node. What do we do with it?
Well, that's where another special procedure comes in, called RB delete fixie-p. Its job is to figure out how to handle this extra black.
RB delete fix a P, the extra black wrangler. Sounds important.
It is.
All right.
So RB delete fixie-p basically has this loop, and it keeps going until that extra black is dealt with. And there are a few ways that can happen. One way is if the node with the extra black is originally red, we can just recolor it to black, and boom, the extra black is absorbed.
So if the node was already red, it can just take on that extra blackness.
Exactly. Another way is if the node with the extra black makes it all the way up to the root of the tree. In that case, we can just get rid of the extra black because it doesn't really matter anymore. The root doesn't have a parent to conflict with.
Right, the root's at the top, so it doesn't have to follow the same rules.
But most of the time, we'll need to do some more work. And that involves looking at the sibling of the node with the extra black and the colors of that sibling's children. Based on those colors, we have 4 main cases to consider.
4 cases. All right, lay them on me. Case number 1.
Case 1 is when the sibling of the node with the extra black is red. In this case, we recolor the sibling to black, we recolor the parent to red, and then we do a left rotation on the parent.
Okay, so recoloring and a rotation. Sounds familiar.
The important thing is this sequence of moves doesn't solve the problem immediately, but it sets things up so that in the next iteration of the loop, we'll be in one of the other cases. Now, case 2 happens when the sibling is black, and both of its children are black.
So everything's black in that part of the tree. What do we do?
In this case, we recolor the sibling to red. And by doing that, we basically move the extra black up 1 level to the parent. So the next iteration will focus on the parent node.
So we're passing the buck up the tree.
You could think of it that way. Now, case 3 occurs when the sibling is black, its left child is red, and its right child is black. In this case, we do a right rotation on the sibling after some recoloring, which sets us up perfectly for case 4. And then finally, case 4 is the one where we actually resolve the extra black issue. This happens when the sibling is black and its right child is red.
Okay, so this is the big payoff after all that setup.
It is. In this case, we do some specific recolorings and a left rotation on the parent. And the net effect of all that is that the extra black that was associated with node X is finally absorbed. The black height property is restored, and the loop ends.
Amazing. It's pretty incredible how these specific color combinations and rotations are like a perfectly choreographed dance, all to keep the tree balanced.
It's quite elegant, isn't it?
Yeah.
And even with all these cases and rotations, the deletion process is still very efficient. Just like with insertion, it all happens in logarithmic time.
Wow. Well, it feels like we've really covered a lot of ground today. We've talked about the fundamental properties of red-black trees, the role of rotations, the nitty-gritty details of inserting and deleting nodes, and how all of that works together to guarantee those efficient logarithmic times.
We've definitely gone deep. And I think we've seen why red-black trees are so fundamental in computer science. They're used all over the place to keep data organized and accessible.
Right. And the chapter we've been discussing, it goes even further, talking about some pretty cool extensions of red-black trees in the problems section.
Oh, yeah, like the idea of persistent dynamic sets, where you can basically keep track of all the previous versions of your data structure as you change it. Red-black trees can handle that.
That's pretty wild. It also mentions AVL trees, which I guess were the pioneers of self-balancing trees even before red-black trees came along.
Absolutely. And then there's this whole zoo of other self-balancing tree structures, B trees, AA trees, tree splay trees, skip lists. It's amazing how many different approaches there are to solve this same fundamental problem of keeping dynamic sets efficient.
It's mind-boggling, and each one has its own little quirks and advantages. Speaking of clarifying things, the glossary at the end of the chapter is super helpful. I always appreciate a good glossary.
Me too. It's great for solidifying those key definitions and making sure we're all on the same page with the terminology.
All right, so to wrap things up, I think we can safely say we've done a pretty thorough deep dive into the world of red-black trees.
Definitely. We've seen how they work, why they're so efficient, and how they handle the tricky tasks of insertion and deletion.
And on that note, I want to leave you with a final thought. We've seen how in red-black trees, these simple rules about color and these local restructuring operations can lead to a global property of balance, a kind of harmony in the tree.
Yeah, it's like each little part of the tree is working together to maintain the overall structure.
So my question for you is, What other areas of computer science, or maybe even beyond computer science, exhibit the same kind of emergent behavior where simple local rules or interactions can give rise to complex and robust global properties? It's definitely something to ponder.
A great question to end on. Always leaves us with something to think about. Until next time.
Happy exploring!